Welcome to the first video of this course. In this video, we're gonna introduce very basic notions that we're gonna use throughout the course. So I would ask all of you to watch it carefully, even if you believe that you are very comfortable and very familiar with the stuff that I'm gonna cover here, okay? It's gonna be important to set the basis, and also I'm gonna talk about things that maybe in a way that you haven't seen as much, some of you. Let me put it like this. There are typically three categories among people who take this course regarding index notation and Einstein's sign convention. There are people who know it perfectly and have used it a lot, and of course, no problem with that, that's perfect. There are also a larger set of people that believe that they know it, but actually not really that much, because usually in courses courses where it's important, it's often typical in physics to abuse this kind of convention and abuse it in ways that would be extremely confusing if we keep the abusing relativity. In fact, it will lead to wrong ways of doing things. So the typical way in which in physics courses index summation, Einstein's summation is applied, which is basically just the plain, repeated indices sum. Well, that is not the way we apply Einstein convention. That's not the original Einstein sum convention and the one that's powerful. And we will see why. Then there's a third category that are not that familiar with it. And either way, I think that it's important that you watch this and you go through this and we establish the common grounds on the notation that we're going to use throughout the course. Okay? Now, apologies in advance if I'm talking to you and you already know it, but I think it's worth still going through it. All right, let's study this convention, or let's introduce this convention in a very simple setup. We're going to talk about vector spaces, and we're going to talk about vectors and linear operators, vector spaces and linear operators in those spaces, that if it's a finite dimensional space, I can represent as matrices, the linear operators. So let's begin with notation that you know. I'm going to imagine a vector v. I'm going to write the arrow for now, although we will drop that notation and write something else. But for now, and not to confuse anybody to begin with, let's write like that. A vector v is a vector in, let's say, Rn, for example. All right. So of course, I always say it's very important to distinguish a vector from its representation in a basis. A vector is an abstract object that lives in a vector space, in this case Rn. But of course, I can set a basis, for example, given a basis of Rn. Let me call that basis a set. It's going to be E1, E2, E3, and so on and so forth, all the way to En. So say that that's a basis. A basis is a set that spans the whole vector space by linear combination, as you know from previous courses. So if I have a basis of Rn, like that with n elements in this case, I can represent the vector as the collection of components, right? I can say, all right, this vector v is equal, of course, as the sum as v1 e1 plus v2 e2 plus all the way to vn en. And I can decide to collect all these components, all these numbers, this v1, v2, all to vn, are real numbers. And these numbers I can decide to collect the numbers, say in a column vector, and put them here, v1, v2, all the way to vn. And this column vector would be a representation, and look that I don't write on purpose an equal sign, I write something else. Doesn't matter what I write here right now. What is important is that this is not the vector. This is a representation of the vector in a basis. Let's say a basis that I call V. Okay, that basis V. So this collection of numbers is the representation of the vector V in that basis. Of course, I mean, typical intuition, right? If I have a vector, let's say that I represent with some direction in R3, like here, the components in a given basis in 1, but if I tilt my head, the components change, the representation changes, but that doesn't mean that it's a different vector. The vector is the same. I'm representing the vector in two different ways. All right. Now, notice that I wrote on purpose the index of the component upstairs as a superindex, and the index on the elements of the basis as a subindex. This is going to be important. Now in this video, we're not going to learn why we decide to write some of them upstairs and some of them downstairs, as in like the notion, what we will call later the notion of covariance and contravariance. That's gonna be the next video. But I'm gonna from the beginning write it like this, okay? Oftentimes you probably are used to seeing it all of them down, but in this course it's gonna be important to distinguish when they are upstairs and when downstairs, superindices, subindices. All right, of course we can write this vector v, right, as sum I equals 1 to n, and then I would have vi ei, right, which is the same as writing that. So keep in mind that I'm not taking, this is the abstract vector, v, this is the abstract vector as equal to a sum of vectors. All of those are abstract vectors in a basis. And this is a representation of the vector in the basis. So let's not confuse, something that is typical also to confuse when explaining that is saying, oh, the index upstairs means a column vector, the index downstairs means row vector. No, I could have represented this with a row vector if I wanted, or with a column vector like this, and still is the same object, okay? So let's not think of associating upstairs and downstairs as rows and columns, because that is not what it is, and it's gonna be misleading. Even though maybe in previous courses you've seen some intuition along those lines, forget it. It's not gonna work. It's not good intuition, in my opinion, and we will see why. Okay. Anyway, so let's define first the Einstein summation convention. What is it? Einstein summation convention tells. So let's write it here. Einstein convention. It says.
Repeating indices, upstairs, and upstairs only put in quotes, and downstairs, sum.
So, by that I mean superindices and subindices that repeat, sum. That's an understood sum. So in this case, right here, this would be the same as saying, this is equivalent, oh my bad. This is equivalent to writing vi ei. So we understood that when we have an index I repeated upstairs and downstairs, that is summing. Of course, this is a vector v, right? A sum of components times elements of the basis. All right? Very well. So important, and very, very important, is to consider that Einstein convention only applies when the indices that are repeated are upstairs and downstairs. If you have two indices downstairs, two subindices, and they're repeated, that is not a sum. That is not Einstein's sum. The proper way of applying the convention is you have something that comes from a superindex and a subindex, and they're repeated, they sum. And there is a reason for that, a reason that we will see much better when we understand the notions of covariance and contravariance. That will be the next video, okay? But for now, let's keep it clear. Einstein convention says that we only sum when we have a repeated index upstairs and downstairs. All right, let's erase the board and go to the next step now. All right, so we have, imagine that we have some linear map that gets vectors from Rn and maps them into vectors in Rn. For example, we apply to a vector v, returns a vector w, all of them in Rn. Okay, so introducing notation. In some bases, forget this for now, in some bases, the components I'm going to write as v superindex a. A runs from 1 to n, so v1, v2, v3, v4, v5 are the components of the vector v in a given basis. Then the vector w, I can also write in wa, a runs from 1 to n, right? And a matrix, if you want, representing so the linear operator a that takes v's and maps them linearly to w's in the same space, I can represent by a matrix, which is a collection of numbers, if you want, that has, and this is interesting because I write, these are the matrix elements of A in a given basis, and those matrix elements, I write an index upstairs, an index downstairs. Now in this video, the difference between an upstairs and an downstairs index, I'm not talking about. So it's important for now that even though I write them like that, and that is actually the way I should write it for now, we're not going to learn in this video what it means when it's upstairs and downstairs. What we're not going to learn in this video is what it means to be on the left and the right. You see that we have one index to the left, A, and one index to the right, B. Now, very important, never copy, unless I tell you so, never copy this as A, B, A over B. It's not true. One index is the first one, another one is the second one. That's going to be important, okay? So keep in mind that I always, even if they're upstairs or downstairs, I always keep the position where they are. In this case, we have a first index that could be up or down, but here is up, the first one. A second index that could be up or down, but it's down in this example that I wrote. Okay? Now, to find out what it means to be upstairs or downstairs, you need to wait to the second video, which is going to be, again, the notion of covariance and contravariance. All right? But for now, bear with me. I represent the components of the vector v. I represent it with v with a superindex telling you what component it is. W, a W with a superindex telling you what component I'm talking about in that basis. And these are the matrix elements of A. Now, as an example, imagine an example in R2, which is very easy to write, even for me. So if I have a vector VA, which has to come, look how am I representing the components in a column vector here. Is 1 and minus 1, so that means that V1 is 1, V2 is minus 1, right? And I have a matrix, AAB, those are the matrix elements, and I put a parenthesis here just indicating that I'm going to write it as a matrix. I have the components AB like 1, 2, minus 1, 0, so that means that A11, first row, first column is 1, first row, second column is 2, second row, first column it's minus 1, and second row, second column is 0, all right? So of course, a matrix in general, if I want to write AB in an R2, that matrix would be, of course, A11, A12, A21, and A22. All right, so what we're gonna do now is, well, what would be the action of the matrix A on the vector V, or the linear operator A on V? Well, let's compute it. So if I have the action of A acting on, this is the matrix, look at the matrix, I write a little serifa here, and the components, I write nothing. So this is the abstract linear operator, and this is the representation of the operator in a basis. Again, same thing as before. Now, A acting on V, of course, I can represent as a matrix with the matrix product, right? So I have, as you know, the matrix 1, 2, minus 1, 0, acting on the vector 1, minus 1. What does that give me? Okay, well, that will give me a column vector, and it will be 1 times 1, 1, 2 times minus 1, minus 2, 1 minus 2, minus 1. And this is minus 1 times 1, it's minus 1, and 0 times minus 1, that is 0, so total of minus 1. So that would be the vector W. So if I call this guy W, in consistence with this, right, W is represented by this vector. This represents the vector W in that basis, okay? So looking at that, we know that W, that basis W1 would be minus 1, and W2 would also be minus 1. All right, so interesting enough, if I were to do it in general, so if I do this in general, what would be the matrix product? And what do I mean by in general? Well, in general, I mean that if I write that W is A, V, and say that in R2, I said, well, A is represented as, you know, as I have it here, A11, A12, A21, A22, and we do the matrix product with V1, V2, what do we get? Well, what we get is that this is equal to, of course, a column vector that is A11, V1 plus A12, V2, and the second one is A21, V1 plus A22, V2. All right, well, what do we notice here? What we notice here is that the second index of the matrix coincides with the index of the vector. And this thing can be written as an Einstein sum, right? This thing is nothing but A1, if you want I, VI, and here A2, I, VI, as two sums, as you can tell. So it's wonderful. So that tells you that the first component is A1, and then A1, I, VI, sum for all values of I, and A2, I, VI, sum for all values of I. So that's wonderful because that allows me to actually write the following. So I'm going to write it here. W component, say A, is gonna be equal to A, B, V, B. And this expression is the same as all that. So what does that mean? What is that? Well, this is telling me that the A component of W is gonna be equal, if I expand the sum, it's gonna be equal to A1, B1, V1 plus A2, V2. If I'm in Rn, I would have n summands, but I'm in R2 in this example. So you can tell that the A component of W is gonna be equal to this sum. And indeed, if we compute it like that, let's use this expression in parallel with what we have here and compare. So let's see what we have in this case. So that tells me that W1 would be equal to A11 V1 plus A12 V2. Is that right? Okay, let's substitute. A11 is 1, so this is equal to 1 times V1, which is 1, plus A12 V2. A12 is 2, and V2, where is that? Yeah, V2 is minus 1. All right, so what I get is 1 minus 2, so minus 1. Right, W1 is minus 1. Yes, that's exactly it. W1 is minus 1. It's the same as I got with the use of matrix product. Now, I write this product very compactly in index notation. Now, notice that calling it I, calling it F, calling it Joshua is the same thing. This is a dummy index. An index that is sum over. I can call it whatever I want. So, very important. A, B, V, B is exactly the same thing as I, VI, and that's exactly the same thing as A Joshua V Joshua. Now, at least stupid to call it Joshua in this case, but it is the same. It's a dummy index. It's the same thing. It's the same as having sum over B, right? And that means that whatever I call the summation index, it doesn't matter. If I change the name of the summation index, nothing changes. That's important to remember. This mistake, many people do a lot. So keep in mind that dummy indices that are sum, don't need to have a fixed name. I can change the name. In fact, I should change the name if I'm already using it for something else in another sum dummy index for a sum. Anyway, that said, very important to remember that, and very important to know that this expression, right, is kind of a matrix product. This is a matrix, a 2x2 matrix acting on a 2x1 vector. Okay? All right. Let's see a little bit more complicated stuff. Let's see matrix multiplication in index notation. All right, so imagine that we have now two matrices that in some bases have these matrix elements. We have A and B here. And we want to compute the matrix product, A times B. So I want to compute what would be the components of A times B, being the dot here, a matrix product, components AB. All right, well, we know how to do matrix products, so let's do it for a sec. We have 1 minus 1, 2, 0, times 0 minus 1, 1, 1. All right? And the result of doing that is 1 times 0 is 0, minus 1 times minus 1 is minus 1. Okay, you got it? 1 times minus 1 is minus 1, minus 1 times minus 1 is minus 1, so minus 2. Then 2 times 0 is 0, and 0 times 1 is 0. And finally, 2 times minus 1 is minus 2, and 0 times 1 is 0. So, minus 2. All right, so this is the matrix products that we're looking for. Now, how do we compute a matrix product with index notation? All right, very easy. To understand how to write this in index notation, let's compute the product of these two generic 2x2 matrices A and B, right? Let's see what the resulting entries are. Well, the resulting entries are A11 times B11 plus A12 times B21. That'll be the first entry. Okay, what about the second entry? Well, the second entry is going to be, we go like that, and then we do A11, B12 plus, so this times this, and now this times that. A12, B22. How about the third entry? Well, let's do the third entry, A21, B11 plus A22, B21. What about the final entry? Okay, so we get A21 times B12, A21 times B12 plus A22 times B22. Aha! So if I call this matrix, say C, C11, C12, C21, C22, then I get that, for example, C11, it's equal to A11, it's copying from here, B11 plus A12, B21. Awesome. Let me point you to something interesting. Oh. 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 and it keeps going. Oh. Oh. So, there's a pattern to it. And the pattern is that always I have an Einstein, in each one of them I have an Einstein sum of a repeated index downstairs and upstairs. Always. And it's always the second index of the first matrix with the first index of the second matrix. If you see, this is an Einstein sum. Imagine that I want the entry C, I don't know, AB. What would be CAB? Well, let me just write it like this. A, C, B, C, B. Is that correct? I wrote something here. Is that correct? That's something I wrote based on the pattern. Let's see if it's correct. Let's find out what C11 is. Well, C11, what I have to do is change the A for a 1 and the B for a 1. And I get that this is A1, C, B, C1. And this is an Einstein sum, so C goes from 1 to 2 in this case. So A11, B11 plus A12, B21. And that coincides exactly with the entry C11 of this matrix. Alright, so look, the index notation, now hopefully you start to see the power of index notation. I can write in arbitrary dimensions, I can write that the entry of the product C, remember that the matrix C is the matrix product of A and B. Okay? So the entries, the matrix elements of C are given by the contraction of the second index of A and the first index of B. These things are the components of A times B, components A, B. Alright? Now it's important that we realize that there has to be always the same number of free indices on the right hand side and the left hand side. How many indices are there on the left hand side? 2. A and B. 1 upstairs, 1 downstairs. How many indices are there on the right hand side? 2. 1 A upstairs, 1 B upstairs. You see, this has to be true. The indices upstairs and downstairs have to coincide. And somebody may say, but there's also an index C. Not quite. That index C is a sum index. It's a dummy index. It's summing. Okay, we are summing over C. It doesn't really exist. It's summed over. It's like saying sum over C, right? So, a matrix product we can write like this. All right, let me clean the board and then write this matrix product in this clean way. And then let's do the example that we had here to show it. And we'll discuss a little bit about changing the order of the product. And what does that mean? That's a mistake that many people do a lot of the time. So watch out for what's coming. Huh? All right, let me erase and clean out this. Sorry. All right, so I wrote the matrix product A dot B, right? And the components ij. I purposefully changed the name of the indices because, again, they're indices. They can call them whatever. It's, what we saw with index notation, is this expression. So I contract, I sum over the second index of the first matrix and the first index of the second matrix. Okay? And let's compare and let's see that indeed I get this result. Well, let's take one entry. For example, let's compute this -2 here. Okay? So that would be the 1, 2 entry. So I equals 1, j equals 2. So if we apply that and we want A dot B entry, say 1, 2, well, I just take this expression and substitute I by 1 and j by 2. So that would be A1, K, B, K, 2. And this is an Einstein sum, so that means A1, 1, B1, 2, plus A1, 2, B2, 2. Let's substitute the entries. We want A11. A11 is this guy here. So this is a 1. B12, B12. B12 is this minus 1 here. So this is times minus 1. Okay? And then I get A12. A12, in this case, 1, 2 is this minus 1 here. So this is minus 1. And then finally B22. B22 is this guy here. So it's a 1. So it's a 1. So total minus 1 plus minus 1 minus 2. So yeah, definitely the right result. This expression works. This is the compact expression to write a matrix product, or the entries of a matrix product in the notation. The trick is a matrix product contracts the second index of the first matrix with the first index of the second matrix, and that's a matrix product. Now, very important, things that people usually do wrong. They say, oh, if I write this, and I write here, this is equal to B, K, J, A, I, K. And then people would say, no, you can't do that. You can't change the order of these guys because it's a matrix product. Yeah, no, you can't change the order of these two guys. You can't. But you can definitely change the order of these two guys because those are numbers in a sum. Now, let's think about that carefully. Is it true? Can I just dilly-dally change, put the B first and the A after? Definitely not here. A times B is not the same as B times A. But if I change the order of these two guys, it's not changing the order of the matrix. These are numbers. Keep in mind, those are entries, those are components, they are numbers. I can move them around whatever I want. You don't believe me? Let's see what sum is this. Let's compute here, again, with this expression, A1, A times B, entry 1, 2. Well, that would be I is 1 and J is 2. So that would be B, K, 2, A, 1, K. And this is an Einstein sum. Remember, repeated index upstairs and downstairs sum. So this thing would be B1, 2, A, 1, 1, plus B2, 2, A, 1, 2. Well, this guy is exactly this guy, and this guy is exactly this guy. So yeah, it's exactly the same thing, minus 2 again. So yes, indeed, you can swap at this level, because these are numbers. It's like numbers in a sum. Remember, these things are like, all right, it's 3 times 2 plus 4 times 5. And I say, oh, is that equal to 2 times 3 plus 5 times 4? And is that equal to 5 times 4 plus 2 times 3? Yes, indeed, it's all equal. And that's what we do when we swap on this side. When things are written in index notation, the order is not captured in, so what is captured by the order of the matrices in the multiplication, in the index notation is captured in what index is being contracted, not in the order of the multiplication. Let's understand that a little bit better by seeing examples of different products and by seeing the notion of transpose. Before continuing here, let me quickly introduce the notion of the transpose of a matrix. All right? Let me erase the board. All right, let me introduce the notion of transpose. Now, the transpose of a linear map is a little bit more involved than what I'm going to say, but I'm going to restrict myself to matrices, which is what we introduce in this notation. Now, imagine that I have a matrix whose matrix elements are these ones, okay, in a given basis. So, for example, 1 minus 1 to 0. What is the transpose? Well, the transpose, as you know, is get the rows and make them the columns, and get the columns and make them the rows, right? It's the same thing. So the transpose is interchanging rows and columns in a matrix, as you know from previous courses. Now, one thing I want you to pay attention to is that in this video, as I said before, but I repeat, you shouldn't care about what's upstairs and downstairs, okay? I'm writing things consistently with the notation, upstairs and downstairs, but that's not the most important part. The most important part is what is left and right in what we're saying here. The first index, by the usual convention, represents the position in the rows. The second index represents the columns. So first index rows, second index columns. Okay, that's what the first and second tell you. The position first or second is important. Up or down, we don't know yet. We have no idea. So this crazy prof is writing some of them up, some of them down. Well, you don't care yet, okay? We will care about that in the second video. But what is important is that the first index is the rows, no matter if it's upstairs or downstairs, and the second is the columns, no matter if it's upstairs or downstairs. All right? Cool. So if you write the components here, we say first row, first column, 1. First row, second column, -1. Second row, first column, 2. Second column, second row, second column, 0. Same here for this one, for the transpose. First row, the first one is always the row, even if it's downstairs. First row, first column, 1. First row, second column, 2. Second row, first column, -1. Second row, second column, 0. Now, you realize that the transpose swaps, so make equal, the entry 2, 1 is equal to the 1, 2 of the transpose, right? And the opposite as well. The 1, 2 is equal to the 2, 1. So we can write that Ij, right, it's equal to A transpose Ji. So you see the operation of transposing is moving the J. If it was on the right, now it's in the left. And if it was in the left, now it's on the right. It preserves, if it was upstairs or downstairs, still is downstairs or upstairs. You don't touch it. The transposition doesn't lower them or raise them. It keeps them where they are. They just swap them, okay? Now, so we see in this equation, this can be read as, right, Aij, I can write as the transpose of A, but then I swap the indices, that undoes the transpose. So you can think of taking a transpose as swapping the indices, left to right, and that's important, left to right, but not up or down, okay? So if I have at some point a matrix Bij, I can always substitute the matrix Bij by B transpose Ji. Same thing, okay? Because I did kind of the transpose twice. You can read it as doing the transpose twice. First transpose, then swapping. All right, we're going to identify matrix. So the exercise that I'm going to do now is identify matrix products from their expression in index notation. So I have here different expressions that look pretty similar, only like playing with the indices. And playing with the indices is the same as in the matrix notation with playing with the matrices a little bit, as we will see. Now, if you don't feel comfortable to try, don't try now. But what I recommend is that after I solve this, you rewind and you pause it and you try to do it yourselves, right? Because it's good practice. Let's identify these matrix products, shall we? Okay. The first one. Well, the first one is very easy because the first one is already in canon form. What is canon form? Well, to identify a matrix product, you always say, okay, the second index of the first one is contracted with the first index of the second. Every time you get that, that's a matrix product. So this one is already in that form. So I know this is the matrix product A times B with a serifa. This is the matrix, right? And the indices, the dummy index is J, the indices that are left is I downstairs and K upstairs. All right. Now, what about the second one? The second one is not in this canon form that I call it. I mean, what I can do is, well, I see that there's a contracted index, J, but I see that it's the first, to write it as a matrix product, to help myself see it, what I can do, I need to write it so that the second index of the first one is contracted with the first index of the second. So I can help myself by saying, okay, I can just swap the order of these two terms, and this is A, Kj, B, Ji, and this is certainly in the form now that I call canon, which is the second index of the first matrix is contracted with the first index of the second matrix, and that is a matrix product and happens to be the same as before, A times B, right? So this thing is the same as the matrix product A times B, only that now the three indices is the downstairs one is K and the upstairs one is I, so it's Ki. All right. Now, I chose this specifically because I don't want anybody here to think that this thing is the transpose of that one. It is not. Because this, you may see that and say, oh, there's an I where it was a K and there's an I where it was a K. That's a convention. I can call them Joshua if I want. They're indices, right? This is not the transpose. Indeed, if I wanted to write the transpose of that, remember, transpose, what it does, the transpose, is swapping, I would have to do this. The entries of the transpose would be this, Ki. You see, it will be very different from that. The first index would be upstairs, even though We haven't seen. So remember, when you transpose, left and right preserves up and down. So this is not the transpose of that. It's exactly the same thing, only renaming the indices. It's like, oh, I give you a matrix AB, but instead of AAB, let me call them JK, and then let me call them BA, but I've done nothing. It's the first entry and the second entry, okay? So certainly this thing is not the transpose of this one, it's actually the same as this one. And you see how it's important to respect upstairs and downstairs now. Hopefully the transpose will be something like that, okay? All right, I mean, this might be not that clear at this point, but it's important to know that this is exactly the same product as that, just renaming the labels. All right, let me erase that and let's keep going. So this is the same. This is A times B, so basically this thing is describing A times B. This is also describing A times B. What about this one? Okay, let me make the line longer, like that. What about this one? Well, here we need to work a bit more, okay? The repeated index here is I, and what I want is, okay, I want the second index of the first one, so the one that's gonna contract the second index, I'm gonna put it first, so B, K, I, and then A, I, J. Oh, I didn't have to work that much, now it is in the canon form. The second index of the first one contracted with the first index of the second one. That's a matrix product. And indeed, this thing is the matrix product B times A. Entry, in this case, the dummy index is I, so it's KJ. Right, so this is B times A. And you see this is different from A times B. This thing, these two things are the same thing, but this is different. And you see, even if the A is first, still still describes B times A. It's exactly that. It's not a model. It's exactly that. This is the product B times A. All right, and you can tell that, of course, A times B is different from B times A. A times B and B times A in the notation matrix form, you will say, all right, B times A is not the same as A times B. That is correct, and you can tell here that this non-commutation of the matrix product is captured with what index contract with what in index notation. Because even though this is not true, this thing AAB, BC is exactly equal to BC, AAB, as I said before, and these two things are representing actually this guy, A times B, okay? Now, if I wanted to write the other, I would have to write B, let's call it like that, AB, ABC, okay? Or if I want, this is the same as ABC, BAB, if I want, and these two things are this object, are the components of this object. So you see, the difference between the two, this is this, and this is that, all right? And you see that the difference between the two is not quite, so if you compare this with that, it's not the order of the A. In both, I write A and B in the same order. It's what indices are contracted with what. The first matrix is always the second index of the contraction in the product. The second matrix in the product is the first index of the contraction. And you can tell here, right? Here, the contraction is the first matrix contracts the second index, the second contracts the first index. I know that the first time that you see these kinds of things can be confusing. Luckily, you can rewind a little bit and check it, okay? So, and check it, by check it, I mean see it carefully until you understand. And of course, always come to the sessions that we will have, in the live sessions that we will have, and ask questions. All right, let's keep going. Let me erase that, and let's keep going. All right, what is this one? Well, let's see. First thing first, what I want to do is to write first the one that has the second index in the contraction. So the index in the contraction is K here. So B, I, K, A, K, J. Oh, well, look at that. This is exactly the same thing as before, is B times A. So this would be B times A, entry, I, J. All right, so this also represents B times A. All right, how about this one? Well, we're gonna have to work a little bit more for this one. Now, B we already see is the second matrix in this multiplication because it's contracting the first index. That's the second matrix in the product. But there's a problem that for the first one I need the second index, and it's like first index for both. I need to move this to the second index. How do I move it? And then I look at the class, and the class tells me at unison, by taking the transpose. So I can take the transpose. Remember what I did before? So A transpose, the AKJ is equal to AJK when you take the transpose. So that will become JK. Remember, the transpose only moves left to right, not up to down. Times B Ki. And now it's in the canon form of a matrix product. Very nice. So this thing is the product of A transpose, oops, sorry, my bad, A transpose times B, which is different from anything we've seen before. And this is the dummy index is K, the free entries are Ji. All right, so as you can see here, this is different from all the other ones that we have, and it's a matrix product of A transpose times B. All right. And finally, let's do one more. Hopefully you get the gist. So this represents, gives you the entries of the matrix elements of A transpose matrix product with B. A quick clarification about this example and also the next one that you're gonna see based on questions that I've received. Now, in the example, we've done this. We've done AKJ, BKI, and of course we transpose A, and then this has the form of a canon product. And then we know that this is A transpose B, entry JA, right? Which is, of course, representing the matrix products A transpose B. Now, notice that the matrix product that I'm considering here, the matrix B, would have elements 1, 1, 1, 2, 2, 1, 2, 2. So the first index is upstairs, the second index is downstairs. So this is the matrix product. The matrix product that we have, I mean, this is an example in dimension 2. Of course, this is for any dimension of the matrices. But we have this B, and the A that we're considering, the matrix A that we're considering, has entries A11, A12, A21, A22, right? So with this B and with this A, which is what's representing these entries that I wrote here, this is that when I do the step that is crucial is the step from here to the matrix product representation, is the matrix product between this matrix A and this matrix B. Notice that in the previous examples, we had an object that had the indices different. What we call the matrix B was a matrix that had first lowered the first index and upper the second index, all right? So for this example and the next, it's very important to make sure that you're understanding when we do from here to here, up to here there's no dispute, but from here to here, it's important that you realize that the matrix B that I'm calling B has these entries here. All right. Now, another question that I got is like, how about if I do the opposite? How about if instead of transposing B, I transpose A? Don't I get something different? Well, let's see. I swap the order of these two and then transpose B, and now it's in a canon matrix product form, which is B transpose A. And then you may say, oh, but A transpose B is very different than B transpose A. That is true. However, realize that the lower index here, the first index, is the I, and the upper index, the second index, is the J. So we have IJ versus JI. We can do a double transpose, swapping the indices and adding an extra transpose like this. And of course, this becomes A transpose B JI, which is exactly the same as we have here, A transpose B JI. So it represents the same matrix products, A dagger B, or A transpose B. Okay? Now, again, very important to remember that the matrix product, when we do the step of writing in terms of the composition of two linear maps, these are the coordinates, the matrix elements representing these two linear maps. I mean, this is an example again in dimension 2. Think of it in n dimension, same thing. But important to remember the index structure that we have. This is for this example and also for the next one. Okay, now back to the video where I actually have much better hair, I realize. Okay, so finally, what we have here, this one, we do the same as before. We already see that A is prepared for a matrix product because the contraction index is I, and A has already the second index being the contraction index. So A is the first element in this matrix product. So we don't touch A. But we need to do something with B because we need the first index to be contracted, not the second. So we need a transpose. So if I do a transpose, I get B transpose IJ. Remember that transpose only moves left to right, doesn't touch up or down. If it was up, still up. If If it was down, still down when it moves. All right, so we see now that this is a Cannon matrix product between A and B transpose. So this thing is A matrix product, B transpose, and then we see the dummy index is I, so this is the entry Kj. Okay, so this represents A times B transpose. All right, so this is as much as I want to tell you about operations with index notation to introduce the index notation to you, an Einstein convention. Very importantly, of course, this is true not for 2 by 2, it's for any dimensions of matrices, right? So in index notation, we write compactly any dimensions. And also, we want to extrapolate this to objects that have more than 2 indices, all right? So you can have 9 indices, and then you can't think, so you have 3 indices. If you want, you may represent it in a basis as a 3-dimensional matrix if you want. There are other tricks, like the Kronecker representation. But imagine, you can have rows, columns, and drawers, right? But if you keep upping up the number of indices, right, then it can be anything, right? It's difficult to imagine in high dimensions. Now, the number of indices is not related with the number of dimensions. You can have 4 by 4 matrices, 4 dimensions in R4, linear representations of linear operators in R4, and they still have 2 indices, rows and columns. So objects with 5 indices can exist in R2, can exist in R7. The number of indices is not related to the dimension of the space, okay? That's very important to remember. Above all, if you haven't seen anything of this before. Now, thank you very much for bearing with me for this. I know that some of you know this thing very well and may be boring, but trust me, in GR, things are going to get complicated as we escalate it. And it's important to follow step by step to set up notation. Anyway, please rewatch this and practice this and get yourself comfortable with index notation and ask any questions that you have in the live sessions. In the next video, we're going to understand what is this business of superindices and subindices. We're going to talk about the notion of covariance and contravariance. But that will be in the next video. Thank you and see you there.